X-ray diffractometer, one of the pivotal instruments in science. Hello, I'm AMAN and before we go into understanding the physics and instrumentation behind this wonderful invention, let's see some history and then why it is important. X-rays were first observed by William Röntgen of Germany in 1895. He was conducting an experiment in his lab, the effects of passing an electric current through gas at low pressure in a tube, which is now known as X-ray tube experiment, and found that the photographic plate near the equipment began to glow. He named them X-radiation as it was unknown at that time. Later, he asked her wife Anna to put her hand on a photographic plate for 15 minutes while he beamed X-rays at it. When she saw the photographic plate after 15 minutes, she exclaimed, "I've seen my death," and never set a foot in his lab again. So this was the beginning of a Nobel Prize winning topic. Many physicists contributed in the making of X-ray diffractometer, but the milestones were set by Max von Laue in 1912 when he confirmed the electromagnetic nature of X-ray by observing X-ray diffraction, and the Bragg father-son duo for developing Bragg's law and studying crystal properties for the first time using X-rays. X-ray diffractometer allow us to study the physical and chemical properties of crystals at atomic scale, given the fact that many materials we found around us have crystalline nature, like semiconductors, salts, other organic and inorganic molecules, or can be crystallized using crystallization process. This becomes of paramount importance in understanding the underlying crystal structure. We can extract the properties of yet unknown crystal materials as well. Now we can divide the understanding of X-ray diffractometers in four parts. First is the sample preparation. There are two types of XRD techniques depending on the sample type: single crystal and powder. We can further categorize single crystal into small and large crystals. The difference between these methods, the single crystal and powder, is scale. As the name suggests, a single crystal analysis is focused on exact atomic positions of a single well-ordered crystal, while powdered XRD characterizes a sample of bulk material. Powder X-ray diffraction is used on microcrystalline powder samples. Powder XRD can be relatively quick compared to single crystal XRD due to the significantly reduced difficulty in the sample preparation step. It can be very challenging to grow high quality single crystals of sufficient size to perform single crystal XRD measurements for many materials, but powder XRD can be performed on much smaller crystal sizes. Single crystal X-ray diffraction differs from powder diffraction in sample preparation and equipment required. Powder samples tend to give rise to continuous diffraction rings like these. In single crystal XRD, discrete diffraction peaks are observed like these. Using a crystal X-ray diffractometer, peak positions can be transformed into a series of coordinates to recover the underlying crystal lattice dimensions or lattice orientation of the sample of interest. The interpretation of single crystal diffraction is much less ambiguous than powder diffraction method, but the challenge in these experiments is to prepare the single crystal samples, which can be often highly laborious and time-consuming process. The methods of preparation for powder XRD are powder grinding, and for single crystal diffractions, thin layer depositions, growing single crystals using single crystallization techniques are used. Then comes X-ray beams. Usually X-ray tubes are used, in which the tube contain cathode and anode at high potential difference. Electrons are emitted from the cathode through thermionic emissions and accelerated through the potential to anode, where they undergo rapid deceleration, and hence we get the continuous X-rays. But instead, if the electrons knock out the inner shell electrons, we get characteristic X-rays, as the electron in higher energy levels come down and emit a characteristic radiation. The energies of these electrons in X-ray tube is usually of the order of 10 to the power 4 or 10 to the power 5 eVs, but we may require higher energy electrons to get higher energy X-rays to probe small crystals or when the crystal parameters are really small. For higher energy X-rays, we have synchrotron facilities. The one we are seeing is the Diamond Light source in England. The electrons are ejected from the E-gun here, which are further accelerated using electromagnetic fields in the booster, till they reach to very high speeds, nearing speed of light, and then they are sent to the storage ring, where due to magnetic deflections, electrons emit radiation of various frequencies, which are captured by the beamline and AND stations for their perusal. Next comes the instrumentation, a bit of engineering, a bit of physics. Here you can see the actual XRD machine. The X-rays come from the left and interact with the sample placed in the middle, and the diffracted beams are detected by the detectors on the right. The basic principle here is the Bragg's law. We have solar and divergence slit to make sure the X-ray beam comes parallel to the sample. The instrument is a real genius. We have many sensors used here. We can see the temperature sensor used to measure the temperature of X-ray tube cylinder, and sometimes the temperature of the sample as well. We may employ pressure and humidity sensors depending on the need of the experiment. The setup employs goniometer and position encoders to measure very accurate position values. Next comes the data analysis part. The data we get from the XRD machine is processed by the software packages such as GSAS, XRD UA, which employ the physics and analytics to provide us meaningful results. The pattern we get on the detectors is the data in reciprocal space, where the points correspond to the square of the structure factor. Here we have taken an example where the peaks are visible and the table corresponds to the processing that we are doing to get something meaningful, the lattice parameters. Limiting myself to this much only, since the complete description would take too long. So after understanding all the four parts separately, we almost know how this XRD thing works. First, we prepare the sample, then the sample is placed in the XRD machine. Depending on the energy of the X-rays, we can use normal XRD machines or use synchrotron facilities. After that, we collect the data using the instruments. Lastly, the data is analyzed through software packages. This is how XRD experiments are done. Along with the known applications, I found that pressure-dependent XRD experiments are really interesting, as changing the pressure changes the crystal parameters, and we can expect some changes in the fundamental behavior as well. Along with some interesting physics phenomena and biomolecule discoveries, it can also be used to develop new energy storage solutions by helping in development of such structures which can hold the energy for long without leakage or charge quickly. Thanks for watching. I hope it was useful.